Right. Good morning, everybody. Welcome to the Ancestry and Diversity Working Group Forum. We are still expecting some stragglers, but I think we will go ahead and get started shortly, just so we have as much time as possible.
Great. Thanks, Clarissa. So, excuse me, I have a piece of food in my mouth that I'm not supposed to be eating. So I'm really delighted. Roxana, just turn on your camera for a second, if you wouldn't mind.
Oh yeah, I will absolutely.
Thank you. So I'm really delighted to be able to introduce Dr. Roxana Daneshjou, who is an assistant professor at Stanford in the Biomedical Data Science. She has her PhD and her MD from Stanford. She was one of these brilliant kids that we all hated when we were growing up. She went to Rice as an undergrad in bioengineering and started her MD at Stanford and then became, and she was a Howard Hughes Medical Institute scholar and received several fellowships. Did her dermatology residency at Stanford in the research track and postdoc in the biomedical data science, working on artificial intelligence in healthcare. And just so people understand this sort of background, it is very difficult to obtain your training at Stanford and then get a faculty position at Stanford. That is a huge uphill battle. So it shows you the depth and excellence of Roxana's scholarship, among many other things. And I have been fortunate to know Roxana for many years, acting as an advisor or mentor, and still continue to do so. And we collaborate now on using AI in pharmacogenomics and ultimately, which will expand out to ClinGen. And so today she's here to talk about AI in medicine and their biases. And I'm sure she will pull some from dermatology, since she is a board certified dermatologist, and go from there. So Roxana, we'll turn it over to you. Roxana, do you want people to interrupt you?
I do. Yeah, I'm happy for people to interrupt me.
Okay, so
Um,
Clarissa, maybe you can monitor or put your hands up if you don't interrupt her.
Yep. I'll keep an eye on the chat, or you can raise your hand.
That'd be great. So Roxana, welcome, and thank you for.
Thank you. Thanks for that kind introduction. So I know that this is sort of the Ancestry and Diversity Working Group, and I think these things all tie together. And the issue of bias in biomedical data sets is very universal, right? Because we have these structural problems in our society with structural racism, with structural underrepresentation and access of various groups to medicine and research. And so I think that I hope you'll see the universality of this. And then I think, AI is really hot right now. And it is, as Dr. Klein mentioned, we're discussing about how to use some of these models for pharmacogenomics and clinical genomics. And there are people using it for genomic discovery. And so I think it's kind of important to think about how these methods and methodologies might be prone to bias. But I'm going to start way back when, and this is all older research, because what the work that I did in my PhD in genetics really illuminated how I approached when I started getting into AI, and why I actually, the first thing I thought about was bias in AI, because I had seen what happened and has been happening in the genomic community. Now, obviously, things are a lot better now. Like, we have groups like this group that care about ancestry and diversity. We have things like the All of Us project going on. Things have definitely evolved and improved since I was a PhD student. And I'm hoping that we kind of see that same shift in AI, because obviously genomics is a more mature field than the field of, say, artificial intelligence has been around for a while, but like deep learning and the era of transformers and large language models and these things, we're like still in the really early days. And so some of the things that are happening to me seem very similar to like the early days of whole exome, whole genome sequencing in terms of like who was represented and what's happening. So this is an older paper, but as many of you know, genome-wide association study data sets have largely been biased towards European ancestry populations. I say European ancestry loosely because, as we know, it can also even be, humans are very admixed. And I mean, European ancestry is a huge group. It's hard to necessarily put people into one group because, as I said, there's a lot of
an RP steam to the roundhouse.
A lot of admixing, but representationally, there hasn't been historically a lot of diversity in GWAS studies. And population-specific variation is important. This is an example from 2014 where we were looking at warfarin pharmacogenomics and looking at allele frequency of CYP2C9 star 2 and star 3 and VKRC1, which were the common variants used in all the dosing equations, the pharmacogenomic dosing equations. And as you can see that, the variants of importance are significantly underrepresented, or they have much lower allele frequencies in individuals of African descent, yet you still have significant variability in that population. So there's certainly genomic factors impacting the dose of the medication in that population, but it wasn't captured by the variation that was explaining the dosage in European ancestry populations. And so one of the studies we did, and of course, you're going to look at this exome number and say, you only did 103 exomes. Bear in mind, this was 2014. We did one of the earliest exome sequencing pharmacogenomic studies, and we found this variant in folate metabolism in African ancestry that was associated with the dose of warfarin that these patients needed. And we found that this variant was really much more prevalent in sub-Saharan Africa, which is why maybe signals had not been seen for this variant before in previous studies that had centered mostly on European ancestry populations. And then we, of course, replicated it. We showed that it led to a lower dose. We looked at functional work showing how it impacts in fact, the FPGS gene, which, as I mentioned, is involved in folate metabolism. So basically, the crux of the story there was that studying diverse genetic populations is important, and that risk variants from predominantly European ancestry populations do not necessarily translate to diverse populations. And then we need to study diverse populations so that we can catch the impact of variants that appear across diverse ancestries. I think this is probably all preaching to the choir with this group, but at the time it wasn't necessarily an idea that everyone was on board. And I think, as I said, the field has matured and changed, and the focus has changed from what I've seen. And so it's just an interesting for me as someone who comes from a genomics background and having watched some of this play out in genomics and now where we are, now to watch it play out in the field of artificial intelligence. So we see the same issue in healthcare AI. But we're still in the early days where there's not a lot of groups that are spending, there's not a lot of national effort for diversification yet. There's not, there's only a small number of groups that are laser focused on the issue. It hasn't yet, percolated up. It may begin to, because many of you may know that President Biden put out an executive order around AI, and he specifically called out equity and fairness in healthcare AI. But I would say, as someone who's been in this space and spoken to the larger tech companies who are developing things, it's still on their back burner. So it was exciting for me to see the government kind of say, hey, this is important. And now there are some efforts like the Aim Ahead project to try to improve, the AI workforce, to increase the diversity in the workforce. Because of course, if you have more representation in the workforce, then they will recognize when they're not seen in the when they're not in their own in the data. So hopefully, we're going to have this fundamental shift. So I'm going to tell, two stories about biases in AI, one from computer vision with a focus on dermatology, and another looking at large language models. And so I focus on dermatology for a couple of reasons. One, as Dr. Klein mentioned, I'm a board certified dermatologist, so I understand the domain very well. And two, it's like very obvious the differences because we're talking about images of lesions on skin. And so skin tone comes into play in the appearance of the lesions. And very early on, one of my colleagues, Dr. Ade Adamson, who's a dermatologist at Dell in Texas, wrote this piece basically before a lot of AI and dermatology even took off, saying, hey, I'm just like a little worried about representation in AI and dermatology. And the reason he had that worry is that historically in dermatology, and this continues to be a problem to this day, our textbooks are not representative of diverse skin tones. Survey studies of trained dermatologists coming out of residency programs show that there's a pretty large proportion that don't feel comfortable diagnosing disease and diverse. So we have a structural problem in the field itself, and then that structural problem could be translated into AI. And indeed, Google wrote one of these seminal papers about developing an AI model for dermatology, and they basically left out brown and black skin. It was it's actually a very interesting process how that happened, because I was one of the reviewers on the paper and I brought it up with the editor. I said, hey, look, if you look in the supplement, they don't have diverse skin tone representation. I think this is a problem, and it was kind of glossed over. And I'm sure this kind of same thing happens in genomics where you see the study and you're like, hey, it's really not applicable to all populations. And the piece was published anyway, and actually wrote a commentary as a response, which was desk rejected within 24 hours. And so then the next thing that happened is that I ended up talking to reporters because I tweeted about it after the paper came out saying, hey, there's no, and so reporters kind of caught on, and that's when the issue actually got attention. So it was very interesting to see the scientific process where. And also I heard that internally people did try to warn them, hey, we need to have diversity in this. And so sometimes your processes that are supposed to help, stop this in its tracks don't work. And so that was kind of a very educational lesson for me in how some of this stuff actually ends up playing out. And now they're focused now because they got so much pushback publicly, they are taking a step back and trying to be more thoughtful about representing all skin tones. So with computer vision, building deep learning models, I just want to give you a mental framework for how this usually happens. What happens is for, whether it's radiology or dermatology, we take data. In this case, we're talking about image data. And most of it's essentially all retrospective data that we have pulled from our EMR systems. And we train these very large models on on this labeled data. And so during the training process, the models learn what features in those images are relevant for being able to distinguish between the labels that we care about. So in dermatology, that might be be whether a lesion is benign or malignant. And then we usually have this held out test set, which the model has never seen or trained on. And we test it on that test set. So that is to make sure that there's no, technically what we're trying to do is make sure there's no overfitting.
Roxana?
Yeah.
Sorry, we have a question from somebody who sent it to me in the chat. If it's okay to ask, they're curious, did you experience any backlash for contacting the press with respect to the article?
That's an excellent question. I posted it publicly on Twitter and the press contacted me. The backlash, I guess, there was no backlash like from the university. They didn't care. I did get contacted by Google. They did have me come into a meeting where they tried to explain now what they were trying to do to fix their issue, which was lack of representation and an algorithm that unlikely worked on diverse skin tones. I offered to help them test their algorithm on diverse skin tones, which they declined. They're very secretive about sharing. They did ask me at the end of the meeting not to talk to the press, but they don't give me, I mean, I was like, look, I'm an academic. Like, I'm going to talk about whatever I think is an issue, and it's not personal. Like, if there's an issue, I'm going to talk about it. So I'm sure that I'm not their favorite person. But, you know, I do think that that's how these issues, there was no backlash, I guess, other than Google not being very happy with me and having a meeting with me. But, you know.
Thank you.
So once you build, so you have this held out test set because you basically want to make sure you didn't overfit to your data, because these models are really good at overfitting because they have so many parameters. The issue is that usually the test set comes from kind of a very similar data distribution as the training set, meaning like the same institution. And so even if there is a held out test set, if it's from the same institution and from the same exact data distribution, there's still probably some of your results that look good, like could be from a little bit of overfitting, because studies have shown that when you take a deep learning model and move it to a new institution, there's usually some performance drop off. And then, of course, if you want to actually check for deployment, really you need to use prospective data and be able to assess the model impact in a prospective fashion where you have no idea what the data is that's coming through, no chance to try to like engineer it to work best. The problem is if there are any biases that go into this data that trains the model, you're going to have a biased model that comes out. And so, for example, we looked at 70 AI papers that were published from 2015 to 2020. The sad part is it's now 2023, almost 2024. And if we were to repeat this study, I think the results would be barely different, having kept abreast of the literature. So the first thing we found, and this is not going to surprise anyone in genomics either, because you're working with healthcare data, is that most of the AI data sets are siloed, meaning that they're not shared. Data sharing is just not very, it's in the healthcare AI data space, in the healthcare AI space, there are only a few centers that really push for data sharing. So here, every purple square is a paper, every circle is a data set. So the green circles are data sets that have been shared, and the red circles are data sets that are not available for sharing. And so number one is the International Skin Imaging Collaboration, which is this, which has like over 100,000 images. And, for the most part, the data is not shared. So that number one, and I love this diagram too, because I think it's like a poster for data sharing, right? Because you notice that like these shared data sets actually lead to multiple publications and they encourage science, whereas the red, data sets that are not shared, basically it's like a one-off paper and probably is that data set's like never used again or ever seen again. So that number one, the International Skin Imaging Collaboration, has 100,000 images from multiple sites using something called dermoscopy, which dermoscopy is just like a $900 fancy magnifying glass. There's like no reason for it to be that expensive. There's nothing that special about it. It literally just magnifies the lesion and like also has polarized and non-polarized light, which helps you see skin structures. And the problem is that it's almost all white skin. And the labels are biopsy proven or from monitoring. So like, what is the label of the data is very important. How you create that label is very important. And in fact, like 35% of the papers we looked at had what I would call a noisy label. And that noisy, if you have noisy label, then your model basically learns noisy labels. What do I mean by noisy label? Well, what I mean is that for something that, let's say you're labeling benign versus malignant, a noisy label, which is actually what tech companies have done, is they ask dermatologists to look at the image and label whether it was benign or malignant. Now, I would like to believe that my training is great. However, the facts are the facts, which are that even with consensus, dermatologists don't necessarily do a good job of labeling. The gold standard for, diagnosing a melanoma is taking a biopsy, getting your histopathology. And in fact, studies have shown that a dermatologist biopsies something like 7 to 8 suspected melanomas before they actually find a true one. So asking dermatologists to be the ground truth is problematic in that way. And most concerning was that most of the data sets in dermatology are likely not representative. So most of the papers, only 10% of the papers included any information about the skin tones that were represented in the data set. And of that 10%, most of them, of the 10% that actually said, hey, these are the skin tones that we used in our model, the majority of them either excluded or underrepresented brown and black skin. So that was kind of the impetus. As I mentioned, there are right now smaller groups trying to build diverse data sets. We're one of them. We built this biopsy proven adjudicated data set. It was a small data set to start with. You may know that when you're training these deep learning models, you usually need tens of thousands of images. And so for us, it was meant more as a benchmark, meaning that it's meant more for people to test their models on, not enough for people to train their models on, though we are hoping to have efforts to create larger data sets that could actually be used for training. And so it was 656 images with balanced representation of Fitzpatrick skin tone. So Fitzpatrick is a 6-point scale that was originally developed for looking at sun sensitivity and how easily skin burns, but is now often used to try to assign, quote, color for these AI studies. It's an imperfect scale. And actually, when the scale was first developed, it only had 3 skin tones and it was all the white skin tones. They added the brown and black ones later. So there's a lot of issues, like at every layer of trying to do this work, there's issues. And like even the scale that we use to label what a person's skin tone is has a lot of problems, but it is like the most used and accepted skin tone scale right now. There are efforts to create new ones. None of them have been fully validated for use yet. So what we did is we actually took the light skin tones 1 and 2 and the brown and black ones 5 and 6, and we matched them on diagnostic category, age of the patient, sex of the patient, and the relative year of when the photo was taken to try to match kind of camera technologies, because these photos are taken in the clinic with smartphone cameras. And then we tested these previously developed algorithms, Model Derm, Deep Derm, Ham 10,000, that all were, published on, had receiver operator curve, area under the curve of 0.9 or better, meaning that they were very good in their publications of discriminating between a benign lesion and a malignant lesion. And we tested them on our new data set. We also tested dermatologists labeling the data and looked at photo quality. So the first thing we noticed is performance. It had a huge performance drop off in general across the board, which is not surprising because, as I mentioned before, many of these models do have some level of overfitting. And when you bring them to any external data set, you're going to see some performance drop off. But what was most concerning to us, and so the red line is worse performance. So the closer our curves get to the red line, the worse their performance, meaning that their performance is almost close to just guessing. We found that there was a significant difference in how the models performed between white skin tones, Fitzpatrick 1 and 2, and brown and black skin tones, Fitzpatrick 5 and 6. And so we wanted to show that the issue what had to actually do with the lack of diverse data used to train those original models. And so we did something called fine tuning, where we took some percentage of our data and we showed it to our model to try to train it to be able to recognize diverse skin tones. So we did kind of this experiment where we only fine tuned on white skin, and we got a performance boost from that, meaning that whatever other factors were influencing the overall performance drop off, such as like lighting conditions or camera differences in camera technology, you could get a boost because it's now seeing some of that new data, but it's only seeing the white skin new data. So you actually still have a pretty big gap between the blue bar and the orange bar. And then the only way to actually close that gap is when you do fine tuning and include diverse data in the fine tuning scheme. So the point of that, which is probably very obvious to this group, but wasn't so obvious to our reviewers initially, was that like the issue is not something else. The issue is simply like you need to have diverse data representation in order for the model to learn how to identify the diseases in diverse data. And there's really no other way around that. Of course, we say in AI that every data set has biases. So like our data set is single center, Stanford Healthcare, tertiary care center. It was only biopsied lesions. So it means that it was enriched for challenging benign lesions, because, and that might be why our data set's just like a little bit harder overall, because we don't biopsy every benign lesion we see in clinic. We often only biopsy benign lesions if we are worried about it, or if there's something questionable, or if the patient really asks us to remove it. And they're clinical images, so they might have some artifacts. So we actually did some analysis to show that there wasn't a difference in performance based on the artifacts. And so we believe in data sharing. And so our data set is available through the Amy Center at Stanford, so people can use it for benchmarking. I'm going to shift to large language models, but I'm going to pause here. This part is a little bit shorter, but I'll pause to see if anyone has computer vision related questions. If not, I'll just keep going. All right. So who's heard of ChatGPT? Nobody? Never heard of ChatGPT before, right? Yeah. So, I mean, we have to realize ChatGPT, I think, is now almost 1 year old. I was at NeurIPS last year when it was released. It was a year that felt like a decade this past year. And it's just everywhere. And there's a lot of people talking about large language models, using large language models, particularly in healthcare. Some of which who have no idea how large language models even work. They think it's magic, they say. In some senses, there's a very black box nature to it. And none of these companies who have created these large models have been forthright about how their sausage is made. So at a very high level, we're going to talk about how they make the sausage, but like we don't know actually what data goes into it. We don't know much about like exactly how they optimize. We just have a very like high level understanding. All the papers that, you know, they put out are just so high level that no one could ever, like it's impossible to technically replicate. Not to mention that these models, we don't know how much they cost to train, but people have said anywhere from, you know, millions and millions of dollars. And no, unfortunately, no academic center has the GPU abilities to actually replicate, even if we knew all the technical specifications, which we don't. We do not currently have the capabilities to replicate what is being done in industry. Now, for most of them, the first training step that happens is this self-supervised pre-training, meaning that the data is not explicitly self-supervised because it's not explicitly labeled with any information, meaning that basically what they do is they take large amounts of text from the internet, from the textbooks, copyrighted material, which is why there's been lawsuits. We actually don't know what they even put into, as I said, we don't know how the sausage, we don't even know what the training data is. No one's forthcoming about what they use to train their model, probably because they are using copyrighted data. And what they do is they basically mask words in the sentences and train the model to be able to predict the next word. So it's like a fancy autocomplete. They basically train this large model to learn to autocomplete sentences. And as it does this, it learns about how human language is constructed, words that often go together, words that often don't go together. And then from there, they do something called reinforcement learning with human feedback, meaning that they, at this point, like there's been no feedback from humans. It's just learning directly from the text, unlabeled data. Then they do a step where basically they have the model interact with a human, like you ask it you give it a prompt and it gives a response. If you've played with ChatGPT, you may have noticed you can do thumbs down, thumbs up. You're giving them free information for how they might fine-tune their model. And so when they get the human feedback, they create this sort of reward function for the model to create responses that are more highly essentially rated by humans. And then the last part of like learning that can happen is sort of prompt-based learning, and that happens at your level. So for example, if you've used ChatGPT, you might say, you might give it an example of like 3 or 4 clinical cases and then say, write me a clinical case in a similar format about, you know, cardiovascular disease. And so it will see how, you know, that prompt examples that you've given and actually, you know, respond similarly. So it's kind of prompt-based learning.
Roxana,
Yes.
quick question. My recollection on these is that in the earlier model, in the beginning, you know, when they're just spitting stuff out at you and they're collecting data, you know, from those responses, there is no information collected about demographics, right,
No.
of the user. So has anyone, I don't think it's available, but I don't know. I mean, clearly that's where a lot of the bias will enter, right? Is depending on who's putting all this in. There have not been studies about that, right? Because to my knowledge, that's all sort of still sort of black box. Is that correct?
That is correct.
Okay.
So OpenAI claims that they actually haven't started using user-submitted feedback for reinforcement learning, and that all the reinforcement learning that's happened has been in-house with whoever it is that they've hired to, and it's like a lot of crowd workers that are not getting paid a lot, sometimes in, you know, other countries. So they claim that. We don't know if it's true. I also conversely see the opposite thing said, saying that like, hey, OpenAI has people on social media that are watching to see like what people post. Because like they are constantly updating the model. And so like, for example, people will find some adversarial attack on the model. And a couple of weeks later, they'll post about it on social media, and a couple of weeks later it'll be gone, because probably somebody saw it and went and tried to fix it. But Terry, I think you make an important point, which is that if they start taking, public reinforcement learning, that could be, depending on the scale, a way for bad actors, if they were giving large scale negative feedback, to actually push models to behave in a certain way. But there's no way to quantify that because, again, we don't know the demographics. We don't know how they're using the information. We don't actually know if they have any filter on how, the user feedback is being used. It's all just a big black box. So I always like to show that how ChatGPT can be very convincing and correct. So I asked it to make a handout on sunscreen, and everything it said was very reasonable, or convincing and dead wrong. So it can make up, citations and facts. These citations don't exist. Green et al. 2019. Because I explicitly asked it to give me citations. It probably is pulling a name that commonly appears in citations, and then a year that goes with that citation. I asked it to write a bio for me. It says that I went to Harvard, which I never did. Very proud of that. And then it says I have a PhD in biophysics. My PhD is in genetics. But then it says like a bunch of things that, may or may not. It says a lot of nice things about me, which I would like to be correct. But, it's just like, if you don't know what the facts are, you may assume, and actually there are many physicians who have assumed, oh yeah, that these citations are real, because they haven't looked it up. And so if you know that I'm a assistant professor of dermatology and biomedical science, you might be fooled into thinking that the rest of what it says is actually correct. But it just sounds I say that it's like the world's best BSer, because it just can like sound so convincing. But it clearly has built-in biases. So for example, there's this sentence completion task where the gender of the individual is not specified. So for example, the patient later referred to his doctor saying, Dr. Schultz thinks I'm doing great. And then ChatGPT says, and I trust his judgment completely. Engineer Smith thinks the project will finish on time. And ChatGPT says, and I have complete confidence in his expertise and ability to manage the team effectively. The student later referred to their parent picking them up from school. And ChatGPT's completion is, my mom thinks I did well on the exam and she was proud of me. So like the parent is a mom, the engineer and the doctor, and then of course the CEO are all male. So it's sort of has baked in societal biases. And so this is actually a study that I should have updated the citation. It's in Nature Digital Medicine. We were asking it questions from this paper in PNAS in 2016, looking at race-based misconceptions of medical trainees. And then we also added some questions about like EGFR, so kidney function calculation, which is not supposed to use race as of 2021, because race is not biological, it's a social construct. So we asked it about genetic factors, it's some stuff that clearly somebody had kind of tuned it on, because there's a lot of, as you guys know, trash out there about the genetic basis of race, which is, race is not genetic. But the model did pretty well, except for Anthropic's model, Claude, didn't do so well, because in one sentence it said, oh, maybe small genetic changes over time led to different. So it's, we were looking at whether it would give responses that would perpetuate like false race-based medicine. So for example, when asked about skin thickness differences, all the models failed. So red is bad. All of them were talking about, you know, differences in skin thickness. When we asked about kidney functions, all of them failed. They were all talking about using race for calculated kidney function. And in the case of like the GPT models, they even tried to justify why using a very racist trope that is not true, saying, oh, there's different muscle masses between races, and that's why we have to have a race-based. So it's so bad that it was like not only wrong, it was actually trying to justify using like debunked racist ideas of why we should do things a certain way. So this is a problem because our patients are, and my patients certainly are, using large language models to ask questions. You know, Epic, which is the largest electronic health record vendor in the US, has partnered with Microsoft to bring GPT-4 into EHRs. There have already been pilot studies, including at Stanford. Mayo Clinic has been testing Google system, like I've never had access to, so we weren't able to test that. You know, it's I will say that I have talked to clinicians who have more experience than me to ask if they've ever seen a technology penetrate the medical system so quickly with so little evidence. Because usually medicine, we're very slow. Like I'm sure you guys know in genomics, like genomics has been around for a while. There have been things that have been validated. There are things that have expert consensus statements. And yet for the most part, like the large academic centers are the ones that are kind of driving genomic medicine. We haven't seen it kind of, you know, percolate into the smaller clinics. There are examples where it has, but I think you would agree with me that things have been very slow versus large language models. It's like you've already built it into the EHR. We don't know how the models are made. There's no transparency around that. We have no established framework to decide whether the model is doing a good job or a bad job. There's no grading scale. Every paper that publishes makes up its own grading scale, including when we've published. We've made up our own grading scale for how to evaluate that. There's just no framework. It's just like the research is just in its very early days. And yet, you know, people are jumping right into implementation, which has been frankly a little shocking for me. I mean, I've even been in meetings with people from the FDA where they're asking, like, how do we operationalize some sort of evaluation framework or monitoring framework? And my response is, what do you mean? We haven't even decided as a research community what the appropriate evaluation framework is. So this is like, the cart is so far ahead of the horse, and I'm not sure why, but like, for example, Epic has already announced that they're going to be putting out generative AI capabilities into their systems and just like launch it into the healthcare system, something like no one will have, you know, tested on a large scale. So it's kind of a little bit, to me, a little bit of a interesting / terrifying time. So my key takeaways are that diversifying biomedical data is incredibly important across all domains. And, you know, of course, being thoughtful in the data collection is very key. And I think that's what this group, you know, has really cared about. And I'm hoping that, you know, some of the lessons that we've learned from genomics, we can bring that into the AI community as well. And wanted to just give you some background because, as I said, AI is beginning to kind of penetrate like every aspect of both medicine and biomedical research. I'll take any questions. That's like the end of my formal slides.
Great. Thank you, Roxana. Does anybody, before I ask a few, have any questions? Saw a hand go up, saw a hand go down.
Mildred.
Hey, thanks, Roxana. That was really informative. I have a question about the issue of sort of, I guess, the domain expertise in these AI teams, and you were talking about the dermatologists and the recognition that dermatologists aren't necessarily the best gold standard. And I remember talking to somebody years ago from Google who was probably working on this dermatology project and who told me that they were so surprised that dermatologists don't all agree and that there is no gold standard. But I guess my thought was that if they had somebody on their team who knew anything about medicine, who had practiced medicine, that would have been really obvious from the get-go. So I'm just wondering what you think about sort of whether there's any recognition that they should have people with some expertise in how the data are generated.
Yeah.
Um,
So this is not a Google-centric problem. And actually, there were dermatologists who were labeling for them who tried to give them feedback. But this is not a Google centric. I think this is a tech culture problem that I see over and over again, where they don't spend time with the domain experts and they just build something. And they don't, not only that, they don't recognize that domain expertise might not just be a physician, because there are physicians on that team, but they're not dermatologists, so they don't understand like whenever someone comes and asks me a question about cardiology AI, I do the best I can. And I said, it's really important for you to talk to a cardiologist because I do not know the nuances of imaging in cardiology. That is not how I'm trained. There might be something that's very obvious that I just don't even know about. And it's a similar problem in dermatology. So I think the problem is that for the most part, a lot of people working in healthcare AI don't have direct experience with the healthcare system, and they make a lot of assumptions about diagnoses. I mean, even when so you're saying there's no gold standard. I think for malignancy, so we can all agree generally that histopathology is needed for malignancy diagnosis, but even pathologists will have disagreements on the same slide. There have been studies on this, but it's much better than having human labeling. We just have to label some data sets ourselves recently. And it's so onerous that it's not really scalable to do it this way. But we had a dermatologist, a dermatopathologist. We looked at the path results together. We looked at the clinical photo. In some cases, we looked at the follow-up notes to see what actually happened, if there was if they were debating between two diagnoses. Like, for example, like if they were debating between two different inflammatory diagnoses. And so, I think people don't recognize the diagnostic process is not so clear-cut. And that's why I think that a lot of these systems, especially from a diagnostic standpoint, are going to need to require having a human in the loop. Because there are some things that are obvious, but many things the medicine, as they say, is still a science and an art. And the art aspect is really hard to pin down for a model where you need to tell it this is the answer, because we might not actually have the answer. But I think your larger point is, and this is true for AI and genomics, AI and anything, is people should not be making these models without having members of the team with the actual domain expertise in that particular area involved in giving feedback. Not later, but from the very beginning of how they were designing, the training data set, the model training, like every step, or even what problems to go after, right? I think a lot of dermatologists are like, oh, we don't want a diagnostic algorithm. And in fact, as of right now, most studies show that the diagnostic algorithms, they improve the primary care doctors. They're not at a point for most of them where they improve the dermatologist performance, because the dermatologist performance is pretty reasonable. Maybe one day they will get to the point where they improve the dermatologist performance. There's one study where the sensitivity was unchanged, but the specificity was improved, so they biopsied less lesions. So maybe we're gonna get there. But again, it was all human AI interaction. The standalone models in real world clinical trials, at least in dermatology, have generally actually had terrible performance.
Okay. So Roxana, I know that it wasn't really a focus per se, but I'm wondering if you could update people on the image analysis, because you guys were developing an app for it so that for updating to improve. Is that widely distributed now, or is it just Stanford local?
Yeah. We built this app that like basically patients submit tons of images to us that assesses the photo quality and gives them live real-time feedback on the image quality so that they can take a better photo. Basically, it's like when you're depositing your check in your bank, gives you feedback saying, hey, this photo is not good enough. Like we did the same thing for dermatology. We built it out. We did a clinical trial. We showed that it was effective. Ironically, like we've been having difficulty with the actual integration into Stanford's healthcare system, which was again kind of it's like, okay, I did a clinical trial with this AI model that we developed in-house. All, the Department of Dermatology says we want it. Like it's been difficult to figure out exact bureaucratic channels to get that to happen, even though we actually got funding, lots of funding from Stanford to test this out. And yet, like, they just put ChatGPT into Epic and they're like, oh, okay. I was like, wait, but that has never had any clinical trial. So that's to me where there's been a lot of cognitive dissonance as someone who's done model development, clinical trials around model development, tried to work within the system to get something deployed that, by the way, has almost zero chance of harm because it's not doing any diagnosis. It's just saying your photo is too blurry. Please take another one. Your photo is too dark. Like move into the sunlight. And yeah, so that's kind of been my experience thus far.
Okay. Well, I think that's important. I mean, oftentimes these things are definitely siloed, and that was an opportunity to, have broader implementation. And I think that, the question becomes, as we think about community practice, and that's something that ClinGen works on, right, is you have a lot of different people uptaking the use of these tools. And so I was hoping that physicians on a widespread nature would be able to effectively use it, because I think that that's when we start thinking about bias in medicine, in particular for health equity. That's where it's needed, so that people just don't make these general assumptions. So I know that there are several groups of us at ClinGen that are working on sort of developing these large language models and testing them out, both from a curation standpoint and et cetera. And in this group in particular, we really are concerned with, how things are labeled and how they come in. And so we appreciate you coming today to give the talk. And I will mention that Roxana is part of this group as well. So you'll see her on a regular basis. Anybody else have any other questions before we give you a couple minutes back? No? Clarissa, you got anything you need to wind up with?
Yeah, just a reminder that we will have our regular ancestry and diversity working group meeting. I believe we still have it scheduled for November 20th. And we will see those of you then. And thank you again, Roxana, and thank you everybody else for joining us. If you have colleagues you think would be great to speak at the forum, please again do send me an email at cjklein@stanford.edu.
Great. Well, thank you everyone for attending this morning. We'll see you soon. Bye.